Then I'll start. I'll just jump right into it. RunX is a one-year-old project now, is under the LF Edge umbrella, and it's a new OCI-compatible containers runtime to start containers as NVM. Now, this is a very short sentence, but it's a bit very rich in information. So what RunX is a container runtime. So it's a bit like RunC, is built to run containers. It's OCI compatible. OCI stands for Open Container Initiative, and is a set of standards between containers components. So RunX, exactly like RunC, complies to the runtime specification. So it's standard compliant. It doesn't just work with one vertical software stack, but it works with any of the ones that are OCI compatible. And it is written to start containers as NVMs. So RunC, when you invoke it, what it does is really set up a set of Linux namespaces to run the new container. So it's basically a chroot plus more things. Instead, RunX, what it does is it will create a new XenVM to run the container. RunX is written for embedded, and you will see why. There are a couple of interesting features that I think are particularly interesting there. It's very simple. It's as small as possible. I mean, it's implementation of runtime spec compliant container runtime. It tried to add the minimal possible overhead, and you'll see how the VM is minimal. And nowadays the term micro-VM has caught on. So I can say that a micro-VM is being created. There is very little inside the VM except for the container to run. So it's not, a large Debian or standard OS system in there. It does have real-time support. So it's actually meant to also be used with real-time workloads and accelerator support. So this is really important. So typically in embedded, you have workloads that both need real time and also direct access to physical resources, such as accelerators in programmable logic or other kind of accelerators. And we can have that with RunX. And secure by default, because again, one of the benefits of running containers as VMs is a stronger form of isolation. The project, again, as I mentioned, started 1 year ago. Is Apache v2 licensed, is in collaboration with Adidas. So it's been open for contribution from the start. We have a couple of external contributions, and the development goes on that mailing list that you see on the screen. So how does it work? So your container get pulled from the network, from the Docker Hub, for instance. It could be deployed via Kubernetes or another orchestration framework. Eventually, the container reaches your host. It goes to containerd. Containerd, just as an example, other OCI-compatible container engines will work. So containerd, it installs the container on your host. So it takes the file systems, the overlays, and unpack them at the right location. So it properly handles the data. Then containerd calls into a separate binary, which usually is RunC, to actually start executing your application inside the container with a chroot and the other namespaces set up. So this is where things differ. So with RunX, the container still get installed by containerd at the proper locations. Everything is as before, but when containerd goes and calls RunC, instead it calls RunX, and instead of a chroot, you get a VM. Now, of course, in order to run a container inside the VM, you need to provide a kernel and a RAM disk. So RunX comes with a kernel and RAM disk pre-prepared to run inside the VM so that you can run the container. These little kernel and RAM disks that are RunX provided are really as small as possible. They're not meant to be a full OS. We are not running, Debian and then inside Debian running Docker again and then running the container. We are talking about a tiny kernel. It's a minimal Linux kernel config, and we're talking about a very minimal RAM disk. This is just a busy box plus 10, 20 lines of shell script to run. So there are a couple of did I miss a slide? No. There are a couple of interesting implementation choices in RunX. I'm gonna go over them. So first of all, it's easy to build. It does only have GCC and make really as dependencies. So it cross-compiles easily. You don't need a full cross-compilation environment. You just need a cross-compiler to cross-compile RunX. And that's because there are no dependencies on Xen libraries at all at runtime. So the runtime dependencies, well, Xen needs to be there, but libxl is not linked against or not called. So instead, RunX calls XL, right, detaching itself from versioning of Xen. So the other runtime dependencies we have is bash, JQ, socket, and demonize. So this is pretty much it. So there is no ties between Xen and RunX version. So you can update Xen and update RunX independently at a different time, different versions. So what other interesting implementation choices is no ingest agent. So like I said, obviously we need a kernel and a RAM disk inside the VM in order to run the container, but these are as minimal, as small as possible. Right? Some other project in this area, what they do is they run a full agent, like a daemon running inside your container to monitor, exchange data, exchange configurations. RunX doesn't do that at all. So it just starts your VM. There is a small version of a Linux kernel, a small version of BusyBox. The only thing BusyBox does is really set up the network, figures out what needs to be executed, and executes it. Right. What else should I say? So there is no ingest firmware or bootloader. So the kernel is booted straight from Excel. So on x86 there would be a PV guest. On ARM it's just a regular guest. There is no OVMF, no grab, no bootloader, nothing. And is OCI runtime spec compliant. So that spec is what we work against. So although we have developed and tested with containerd only at this point, it is supposed to work with any other OCI runtime spec compliant container engine. So yeah, so this is an example of how you would build RunX on your box. You set, the arch variable to set the target architecture. You set the cross-compile variable if you are cross-compiling, and then you call build.sh, and that's it. There is nothing really else that you need to do to prepare. From the runtime point of view, it depends on the containerd version. So first of all, you need to install the RunX live scripts and binaries to user share RunX on target. And then basically it's just a matter of telling containerd to call RunX instead of runC. And there are a couple of ways to do it depending on the containerd version. On older containerd versions, you can do it on config.taml. That is a configuration file of containerd. On newer containerd versions, you can do it on the command line. So one thing that is new, recent actually of the last few weeks, is we added a CI loop based on GitLab CI. It's based on a Raspberry Pi instance, and it's just running a test based on QEMU to run, and Alpine Linux is DOM0 to run, RunX inside. Right, Bruce.
All right. Hopefully I'm unmuted. You can hear me. You can nod, Stefano, if you can hear me. All right, good. Yeah, so my part of this that I've been helping Stefano and the developers with is, as you can see from my T-shirt, I'm a Yocto guy. I maintain the meta virtualization layer in the Yocto ecosystem, which includes all of the Xen and Xen tools and support around that. I maintain it in the sense that I merge it. It's actually Christopher Clark and others that tend to send the updates. So I pull the trigger, but they send the changes, to be clear. But what I did do is I created the RunX recipes and integration in the meta virtualization layer. And the question is, it's to try to give us a more structured way. When you're doing development, as you can see, at my second bullet, if I jump ahead, that you can always do development directly with the upstream elements that Stefano was talking about, right? That's always possible, and in fact, it's encouraged. But if you are building, say, in an embedded image, or you need some sort of extra process around it, we wanted to make sure that we had a Yocto integrated build and ability to do that. So, the question would be, why would you do this versus just getting your cross compiler and building it? So the big thing is that we can leverage all the things that you get out of Yocto and OE Core, which of course, if you're deploying, you're going to production with this, things like the configuration of it, the license management in particular, you get your cross compilers built and deployed. You can build SDKs. You can really craft the different elements of your booting system, whether it be the different domains or the host, and of course you can do performance tuning. So I mean so there's all these things that are just part of the Yocto and Open Embedded build process that we automatically get. And of course it does let you transition from development to production, meaning you can use it for both and use a process around that. And as I hinted at with talking about meta virtualization, we do have an active community that are both maintaining Zen and sending upgrades, and we're fixing bugs, and we also get some BSP support. So we have Raspberry Pi 4, and I added some Xilinx target support to meta virtualization. So you can leverage those BSPs, and you don't have to go fetch and figure out those parts in isolation from what you're trying to do with both Zen and RunX. And then there's something a little bit newer in Yocto called multi-config builds. And that allows us to sort of have a single defined system that we can build the host, the guest, the containers, and the firmware sort of all in one pass. And you get all the deployed elements, which I'll show. I have some slides that show some screen captures of that. So you get everything in one place, and then you can create your system from there. All right, that's good for that one. So I wanted to go over just a little bit to be clear for anybody who's not familiar with OE Core and the layers in the ecosystem. So it's built of layers, and so the layers that you include in your build define your platform and what software stack you might be building. So there's a distribution, there's references for that, there's configurations, there's packages, there's image recipes. There's plenty of resources out there to understand what that is, but that allows us to customize and specify all the details. Now, when looked at from the RunX point of view, we get the OE Core, the very lowest level. It provides all of the base support. So that's our tool chains, the base packages, how we construct the image, whether it be partitioned or and the bootloaders and all that stuff. It's built out of OE Core. The meta virtualization is what gives us all of our container runtimes and support. So that's RunX, that's Zen, the supporting components, Containerd. And I mentioned that I just actually finished this week upgrading Containerd. So if anybody is inspired to go try to build this from Yocto, I still haven't retested RunX there. So you can find us on IRC to report problems. But all of those bits are all on that same layer, so we can build everything you need to bring it up. And of course, Zen and U-boot, everything, it's all in meta virtualization defined there. And of course, there's BSP layers where we can pull in dynamically the right kernel, bootloader, and all the things that you do there. So you don't have to think about that stuff when you're trying to compose it through Yocto. And again, you have your own workflow, and that's fine, but we're trying to provide sort of a one-stop shop for these builds. All right. Yeah, so this is just an example that I did last time just to show. I'm not going to read it. I'm not going to go into much. I usually say that and then I proceed to read it. But this is, I would say, use master or hardknot, which is the previous release. Master, again, it's the Containerd upgrades and some of the things that we haven't fully retested yet because it's the development branch. But this is just showing how some of the tools, what you would clone and how you would add the different layers that we need to build for the ZC 102 Zinc MP platform. And of course, I'm still working on making this a little bit easier. We can do a Zen distribution with a sort of a CAN configuration, but these are some of the config things that you might have to do, you know, defining the image type you want, tar, gz, CPIO, U-boot, you know, different components that we knew. There's some tweaks to build that are specific to the Xilinx platforms, and some details about running QEMU later if you want to test it. And I even have a multi-config example there where we're building the PMU firmware along with the main image. And finally, maybe about of interest is, so I guess, yeah, this is actually the build. So there's a few steps that are specific to the Xilinx platform that you have to do. We won't get into the details there, but the big thing is you make two things at the bottom: core image minimal or Zen image minimal, and that will build all of the things that I've been talking about that you need to get an up and booting system. And I think the last slide I had is some example of, you know, this is the outputs of the build. They drop into this deploy directory for your machine, and you can see some of the sizes of things that we got there, right? So we ended up with a 76 megabyte U-boot image for you know, Zen image minimal. There's a root file system for the main system, as well as building the kernel and U-boot. So it went through and built the things. They're the sizes you would expect. You could do more tuning and make those smaller, but we make these sort of generally useful versus really tiny by default. You're muted, Stefano. Yep.
Yeah. Yep. So the tarball contains the entire rootfs, including Excel and all the utilities. Did I skip this slide, Bruce?
Oh, that's me again. Sorry, I thought that was my last one. I totally tuned out there to listen. But yeah, this is just an example of how we don't need you don't need a hardware target to actually test this. You can actually run it inside of QEMU, and you can do all of your RunX testing, and we can integrate it into a pipeline or do whatever we need to do. So yeah, this is an example using the Xilinx provided QEMU, so you can get the Xilinx platform support. But it's that simple to get up and running. And oh my goodness, and this is some U-boot configuration. Again, it's there for reference only if you're working through it. It's what you would expect to do on any target, to arrange the different components to where they need to be. And Stefano has tools and different things that he could point people to actually generate some of this. So you don't have to go write this by hand, but I wanted to dump the details into the slide.
All right. So we discussed again how it works with traditional containers. The more interesting thing, is what it does with non-traditional containers. And that's what really RunX, I think, brings to the table. So if you see here, the container is not anymore the isolation boundary. The isolation boundary is, in fact, the VM. So it wouldn't be much of a stretch to use a different kernel or a different RAM disk if we're coming from somewhere else, not just the one that RunX is providing. And in fact, we support in RunX the ability to run a kernel or a RAM disk that comes with the container. So if the container comes with a kernel binary inside or a RAM disk inside, RunX would be very happy to use that instead of its own. Because after all, that's not the security boundary, right? So the security boundary is the VM. So this is useful for a number of reasons. For instance, you can imagine a container that has some direct hardware assigned, and you see how it was going to be possible soon. And you might want a specific kernel with a specific kernel driver, a specific kernel version, whether it's RHEL or SUSE or something else. Or even more interestingly, you can have an RTOS. So you could take FreeRTOS, you could take Zephyr, package it as a container, and then RunX will see that there is a kernel, there is a flag in the manifest, takes it and run it. So now you can package RTOSes as containers, push them to the Docker Hub, get them delivered through Kubernetes, and automatically, started at runtime through RunX. How does it work? So it's basically the ability of identifying kernel and RAM disks present in the container and using those inside the VM that's been created. It can be anything from a special kernel version like Linux RT or non-Linux OSs such as a bare metal application, unikernels, VxWorks, and so on. So we use at the moment two special flags, RunX kernel and RunX RAM disk, to specify the presence of a kernel or a RAM disk. But we intend to work with the OCI community to get a standard that could be used also for other projects. So the next step is to do device assignment. So it's especially useful when with an RTOS, right? Typically you need to drive something. So the idea is that we can assign directly resources to device direct assignment to these new VMs. And that is done through another special option. This is called XLConf. This today is not requested by the container. It's not possible for a container to say, I want please an accelerator for AI workloads, for instance. It's the administrator that will decide that this container will get an accelerator. The ability of the container to specify the need for an accelerator is on the to-do list, but not yet done. But what you can do today with XLConf is basically you can override any kind of options that RunX will generate for Excel. So you can use it for not just device assignment, but also change memory allocation, vCPU allocation, all sorts of things. So the vision, as I mentioned, is that you will get a container with not just its own kernel and RAM disk, but also a request for a specific accelerator. And if the accelerator is in programmable logic, it could even have the bit stream to be programmed in the FPGA itself. Then we will get programmed in the FPGA, and the container will contain also the software to use it. Okay, I think I covered it. So I wanted to show you quickly a demo. Let me get a chance to do that. So here is, I need to first do something else. So what I did here, this is just a normal DOM0 running. I am about to start containerd and import a couple of containers. One of them is, and you see now, but it was covered by the line, but it's this is what I started, which is going to run on a separate UART. So just a second, you see some interaction. Here you go, some latency measurement done on a separate timer on my Zinc MP board. Switch back. So what did I do here? I started a container using containerd CTR, which is a command line utility. I passed a special XLConfig option to do device assignment. The application is really a bare metal application. It's not even Linux, it's a tiny bare metal app. And that is all there is to it. So I can show you the XLConfig. That's what it is. Right, I'm changing memory allocation down to 64 megabytes. I don't need all that memory. I am changing our queue number. I'm assigning some 4 interrupts for our queue numbers to do assignment of the TTC timer and the UART and the relative memory regions, and that's it. So I can also show you VxWorks running. So here is VxWorks being packaged as a container and being run right here as a VM. And this is VxWorks 7. All right, we have only a couple of minutes left, so I wanted to try to, I saw a lot of questions, so I wanted to try to address some of them. So there is a main difference with Kata containers. Kata containers is a project was started a lot earlier, back when there wasn't really an OCI runtime spec. So back then, if you had to do something like this, you have to start basically almost an entire fork of Docker, and that's how Kata containers started. So starting RunX years later, at that point, the OCI runtime spec specification was already published. It was a lot easier to implement something like this. So we didn't have to touch the containerd code at all, or any other code, so just replacing the runC component, which is a separate component and meant to be replaceable, right? The other difference here is the focus on device assignment and real time. So thanks to the ability of changing parameters of this VM being started, you can select, you can use the null scheduler, you can select, you can ask for vCPU pinning, you can do all sorts of things to make sure that your containers get executed with real-time properties. And finally, of course, the device assignment and the ability to specify a kernel, I think is really important. Many applications embedded are non-Linux. We do want to exploit the powerful container infrastructure, not just for traditional Linux user space application, but also for bare metal and other things. Any other questions? Yeah, I think I'm scrolling through the history. It does start a new VM every time. So the VM are not reused. These are tiny, small VMs created on purpose for each container. It should integrate with any OCI compliant infrastructures quite easily. And it does work with PV code, but that's optional. It depends on the networking model chosen for the container. So yes, PV codes is one of the networking options. The interest of putting Zephyr in a container is because if you're going to deploy Zephyr at runtime, not statically, or just want to update Zephyr later, it's a lot easier to do if you can do it through Kubernetes, if you have 100,000 hosts where you need to update Zephyr. So it's all about scale, right? So in IoT, some deployments are in the thousands. So if you think that you want just to update Zephyr, or you decide you want to add one Zephyr instance to your 1,000 IoT devices, it's a lot easier to do it if you can do it through an orchestration engine instead of having to SSH to each of the 1,000 instances one by one. How is the packaging of VM? I do have a demo of that. So I'm sorry, I realize I'm already over time. It's only going to take 30 seconds. I can show you how that bare metal application was packaged. And this is the Docker file. So it's starting from Alpine. It doesn't have to use this just to start from something. It was just the easiest thing I had already around. I copied the binary, the bare metal binary inside. And I set the RunX kernel environment to make sure to flag the kernel properly, and that is it. I hope I addressed your questions, and if you have more, I'll be in the hallway conversation room. Thank you for attending.